Assalamu alaikum dear students. So today we are going to start a new topic in chapter 5, and which is about the definite integrals. It covers the section 5.3 of the chapter. So chapter 5 continues. Let's have a look at the summary of the section. So in this section we are going to try to find the limit of general Riemann sums as the norm of the partition of closed interval AB approaches to 0. And secondly, this limit process allows us to define the definite integral of the function over a closed interval AB. Okay, here is the definition. So let's see the terms used in the definition. So first of all, we need to have a function fx defined on the closed interval. So this is very important. This is defined everywhere on the closed interval. So we say that the number j is the definite integral f over ab, and that f is the j is the limit of Riemann sums. And you are familiar with Riemann sums. This is the height of the function at some point ck in the kth interval, xk minus 1 xk, and this is actually the width of the interval. This is height, this is the width of the interval, or length of the interval, you may say, or width of the rectangle, kth rectangle. We are now going to try to minimize the length of the interval, or actually squeezing it to 0. So how can we do it? We can do it by squeezing our norm towards 0. So norm is the maximum or the largest length of the interval in the partition P. Okay, so let's read it again. Let fx be a function defined on a closed interval AB. We say that the number j is the definite integral of f over AB, and that j is the limit of the Riemann sum if the following condition is satisfied. So given any number epsilon greater than 0, there is a corresponding number delta greater than 0, such that for every partition of closed interval AB with norm less than norm of P, norm of partition less than delta, and any choice of ck in xk minus 1 xk subinterval, kth subinterval. So you are already familiar with this delta and epsilon structure in the concepts of limit. If we are required to find the limit of a function, like you may say, let me draw here. If we have a function like this, and we have to find the limiting value of the function, say this is the point A. So what we used to do, we draw an interval here. So this is the minus delta, and this is the plus delta, and similarly we draw rectangles here as well. This is the minus epsilon part, and this is the epsilon part, and so same concept is applied here, but in this case this is the rectangle, and we are trying to squeeze its width to 0 by letting this norm approaches to 0. So j is called the definite integral over the closed interval. Now in the limit case, now if this is the graph of fx, so in the limit definition, this structure allows us to write limit of fx as x approaches to a, if this point is a and this point is L, is equal to L. Okay, so following this notion of epsilon delta, we can write that j is equal to the limit of this sum as the norm of P approaches to 0. Okay, now in this case you can see that what happened here, this epsilon delta definition can be written as fx, sorry, fx minus L is less than epsilon whenever x minus a is less than delta. Okay, so here p minus 0 is less than delta. That is norm of p approaches to 0, right? So this is the definition of the definite integral. Now, if this sum is considered for the partition of equal widths, then Sn is equal to this. So this is the two different forms of the Riemann sum. And for equal widths of rectangles, we have j is equal to limit of this Riemann sum as n approaches to infinity. So n approaches to infinity means the number of subintervals approaches to infinity, or the number of rectangles are infinite. Okay, so for equal width subintervals, norm of p approaches to 0 means n approaches to infinity, that is number of intervals is infinite, or the number of you may say rectangles is infinite. So we have the definition of definite integral for equally spaced subintervals is given by this expression. Okay, if the definite integral exists, then instead of writing j, and when does this definite integral exist? When this limit is defined, of course. Okay, if this limit exists, then this definite integral exists. The limit exists means that the right hand limit, left hand limit must be the same, that is upper sum and the lower sum must approach towards the one value, and which means that the limit exists. Okay, if the definite integral exists, then instead of writing j, we write it as the integral from a to b of fx dx. Now this fx is same fx. If we compare it with Riemann sum, this is replaced by actually fxk in Riemann sum, right? So it was delta xk, and this is squeezed to 0, and this integral sign is quite similar to s because this represents the sum of area of infinite number of rectangle in the interval AB. So this is the integral sum, this is the upper limit of integration, this is the lower limit of integration, this is the function to be integrated, that is the integrand, and this shows that we have to integrate with respect to the variable x, and we read it as integral of f from a to b. Okay, so formally we can write the definition of the definite integral, that is integral from a to b fx with respect to x is the limit of this Riemann sum as n approaches to infinity. And you are already familiar with this notation, and we have discussed in detail in the last lecture. And this representation is for of Riemann sum is for equally spaced subintervals, that is the subintervals of equal length. Okay, there is the theorem on integrability of continuous functions if a function f is continuous over the interval ab, or if f has at most finitely many jump discontinuities. Okay, so either it should be continuous on the whole interval ab, okay, or if f has at most finitely many jump discontinuities, then the definite integral of AB of function fx from a to b exists, and f is called integrable over the function a. Okay, so here is an example. The function fx is equal to 1 when x is rational, and is 0 when x is irrational. Now we have to prove that this function has no Riemann sum over the interval 0, 1. Now, since value of the function is 1 when x is rational, value of the function is 0 when x is irrational, and keeping the fact in mind that between any two numbers there is both a rational number and an irrational number. Whenever we have two real numbers, there is a rational number and there is an irrational number in between the real numbers. So the function jumps up and down too erratically over the interval 0 1 that it's not possible for us to find area under the curve or to draw the rectangles under the curve, or even of a very small width or very thin rectangles, but it's not possible. And we can prove this fact by taking the upper sum, and you can prove it yourself, that the upper sum of for this function Riemann sum is like this: f of ck delta x k. Now, if we have an interval, so what is this? The product of the height and the length of the kth interval. So height of the function in the kth interval and the length of the kth interval. Now, if we are considering the upper sum, so maximum height of the uh, function in the kth interval xk minus 1 xk will be 1. Okay, so this sum will become k raised to 1 to n 1 delta xk. Since delta xk is very small, so this sum will become 1. Okay, similarly we can find lower sum. So lower sum will be, apparent representation will remain same, k raised from 1 to n f of ck, but this time we are going to find the smallest height of the function in the kth interval. Okay, it will be 0, because function has only two values, either 1 or either 0. So maximum will be 1 and minimum will be 0. So k raised to 1 to n, and f of ck in this case, in case of lower sum, is 0 and this is 0. So upper sum approaches to 1 and lower sum approaches to 0. So the limit does not exist, and it means this function has no Riemann integral over the interval 0 1. Now, when f and g are integrable over the interval ab, closed interval ab, the definite integral satisfy the rules in the table given in next slides. So we have two functions. Okay, so both the functions are integrable, and we have already know the property of the function which are integrals, that is, they should be defined, they should be continuous, or they are having finite number of jump discontinuities in the inter. Okay, then the function is integrable over the closed interval AB. Okay, here is the table. So first property is order of integration. If we change the order of integration, that is b to a, that is integral of b to a fx dx is equal to negative of a to b fx dx. So this can be proved by the Riemann sum and by the definition. Zero width interval. If we take the integral from a to a fx dx, so what is the width of the rectangle then? The 0. So this integral will be 0. Constant multiple. So integral from a to b of a constant multiple of the function f, that is k fx, k here is constant, dx can be written as k outside, we can take it out of the integral, and of a to b fx dx. Sum and difference, if we have integral of fx plus gx or fx minus gx, it can be written as the separate integrals, sum of separate integrals, or the difference of separate integrals. Additivity, if we have an interval AB, okay, and there is a point AB then we can split this. A to B plus B to C is A to C, okay? Or this can be written as, in case, according to this definition, if we have interval C and B lies between A to C, we can split it as A to C, B to C, A to C, I mean A to B, B to C, okay? So maximum minimum inequality, if f has the maximum value, uh, if x has maximum value max f, okay, and the minimum value minimum f on the closed interval ab, then this integral of fx from a to b lies between the maximum value multiplied by b minus a and the minimum value multiplied by b minus a. So this is less or equal to maximum value of f multiplied by b minus a, and this is greater or equal to minimum value of f multiplied by b minus. So we can we'll just visualize these in the next slides using the diagrams. So domination is if one of the function is greater than the other function, that is if the function dominates over the other function, then the same relation is between the areas, that is same relation goes along the integrals of the both the functions on the closed interval ab. So this is the special case of this. Fx is greater or equal to 0, then integral from a to b of fx is greater or equal to 0. So let's have a look at the graphical representation of these rules. So first here, the zero width. As I told you that when we have integral from a to a, so we have a rectangle of zero width. So its sum is going to be 0. Sum of the product is going to be 0. So this is 0. Constant multiple, if we have the function y is equal to fx, so and let's take the constant k is equal to 2. So what's going to happen? It will be if this is y is equal to fx, so this height will be doubled. So initially, if we have uh, fx height, then when we multiply it by 2, we will have the height double. So area will be doubled uh, under the curve. Okay, so that is why 2 times integral from a to b fx, or k times integral from a to b fx, because heights of the rectangles will be doubled in every interval. So in this way, when we add up all the areas of the sub rectangles, then this will become double of the original area. And this is the sum rule. Okay, if we have y is equal to fx, y is equal to gx, then this will be the fx plus gx. So again, this demonstrate the rule, addition rule, and similarly we can have the subtraction rule. Now this is the additivity of for the definite integrals. If this is the interval AC, as I told you before, if this is the interval AC and we have a point B between the interval, then the area under the curve from A to C is the area under the curve from A to B plus area under the curve from B to C. Okay, so above x-axis, of course. So this is how it can be split. So a to b fx, integral from a to b of fx from a to b plus b to c is equal to integral of fx from a to c. Now maximum minimum inequality, this is quite interesting. Okay, so this is the function and it has maximum value, it has minimum value. So this is the maximum value of the function, this is the minimum value of the function. So this lies between, actually area under this curve the is less than the area of the upper rectangle, okay, and area under this curve is greater than the uh, area of the rectangle in green color, right? So there are two rectangles, the upper one, this one, and what is the area of this rectangle? Area of this rectangle is this height multiplied by width, and height here is the maximum value of the function, that is max of f. and width is b minus a. So area of this rectangle is maximum value of f multiplied by b minus a. And this is greater than the area under this curve. That is, this is greater than the integral from a to b fx dx. Right? So, now this rectangle, if we consider this rectangle in green color, what is the area of this rectangle? This is minimum value, because height is minimum value of f, and multiplied by the width is b minus a. Okay, and this is less than the area under the curve. So this is less than the area. So this is the relation between the maximum value, minimum value, and the integral of the function from a to b. Domination, you can see that if fx is greater or equal to gx at some point, it can be equal. So the area under the curve fx above x-axis from bounded by the lines x is equal to b is greater than area under the curve gx above x-axis bounded by the lines x is equal to a and x is equal to b. So this relation holds. So this is the graphical representation of all the uh, properties. Okay, next definition, area under the curve, which we talked about in previous slides as well. So we are now going to define it in formal way. So y is equal to fx is non-negative and integrable over a closed interval AB. Then the area under the curve y is equal to fx over the interval AB is the integral of f from a to b, because this integral is limiting value of the Riemann sum, and we used to find the or approximate the area under the curve above the interval using the Riemann sums. So area is defined by this interval. So area under the curve, that is, if we have a curve and this is a, this is b, so this integral actually represents this area. Okay. Now, example, compute uh, integral from 0 to b dx, that is our fx here is uh, x, right? And a here is 0, b here is b, and find the area a under y is equal to x over the interval b greater than 0. So let's try. So first of all, let's have a partition, and we are going to have a partition of equally spaced intervals. So in equally spaced case, delta x is equal to, that is length of the interval is equal to b minus a over n. A here is 0, so b over n. So length of the subinterval will be n. So our the t in this case is going to be 0, b by n, that is x naught, x1, and so on, 2b over n and 3b over n up till nb over n, that is the last point must be b. So sigma, so first we'll find the sum and then we'll take the limit, okay, in order to find the integral. That is f of ck delta x. Now the question here is that what is f of ck? So first of all we have to find the ck. Then we will find the value of f of ck. Fx here is, as I told you earlier, fx here is x. So what is ck? You can see that c1 is b over 1, c2 is 2b over n, and similarly c3 is 3b over n, and so on. So if we are going to take the right sum, then ck is going to be KB over n. We can find it for left sum as well. You can try it yourself. And this is equal to, now plugging the values into this sum, we have k varies from 1 to n. Now f of ck, fx is x, so f of ck is kb over n. F of ck is ck actually. So kb over n into b over n. Okay, this can be written as, so let me draw a line here so that we can uh, save the space. So k varies from 1 to n, and this becomes k b square over n square. Okay. Now b square over n square is independent of k. So by the properties of sum, we can write it as constant multiple of the sum. B square over n square sigma k varies from 1 to n k, and from previous section we know that sigma k is equal to n into n plus 1 divided by 2. Okay. Now this can be written as b square over 2 n into n plus 1 divided by n square. Okay. Or this is equal to b square over 2 into, so n, we have n plus 1 divided by n, and n over n is 1 if we divide it, so plus 1 over n. So this is the final form of this sum, this right sum. Okay, now integral of 0 to b of x dx. So by definition, integral is the limit of this sum as n approaches to infinity. Okay, as n approaches to infinity, that is, we're going to write here, so limit of b square over 2 1 plus 1 over n as n approaches to infinity. So this is b. So pardon me if you cannot read my writing properly. So this is equal to more. This is b square over 2 plus 1 over n. As n approaches to infinity, 1 over n approaches to 0. So we are left with b square over 2. So this is it. This is what we are going to we wanted to prove. So here is the proof. So similarly, you can find it with the left sum as well, and it's your exercise. If you can try it yourself, and the answer will be the same. So here is the figure of this function y is equal to x. Okay, so this is 0, this is b, b is any number greater than 0. Now this is the area, in fact, under the region. This is the area. Okay, the whole shaded area in blue. This is the area under the region, and which is equal to b square over 2 by the definition, because we just defined that area is equal to a to b fx dx over the interval ab under fx. So area is equal to b square over 2. Okay, with the help of this example, we can generalize few things. Integral from a to b is a to 0 plus 0 to b. Okay, and this can be written as 0 to a, negative of 0 to a plus 0 to b. And we actually just evaluated integral from 0 to b x dx is b square to c. So this is negative a square over 2 plus b square over 2. And this means integral from a to b x dx is b square over 2 minus a square over 2. And it makes sense. In fact, using the area definition, this is integral from a to b is area under the curve from 0 to b, and area minus area under the curve over the interval 0 a. So it makes sense. Area of this region, area of this triangle, right? Area of this triangle, this whole big triangle, minus area of this triangle, smaller triangle. Okay, area of this triangle is bigger triangle is b by 2, b square by 2, and minus a square by 2. So geometrically, it makes sense. Okay. Uh, Again, there are a few more consequences of this example. A we have already discussed. B, the definite integral gives the negative of area of this trapezoidal region. So this is the figure B, and this is the trapezoidal region. So this is actually negative of this region. Okay. So if we have area in the negative terms, actually we have to take the absolute value because area cannot be negative. It is negative of the area bounded by the curve and the interval and the lines x is equal to a and x is equal to b. So in this case, we have the definite integral gives the area of the blue uh, triangular region added to the negative of the area of the gold triangular region. Okay. So these results can be proved. You will do yourself. Okay. So these are practice problems for you. This is just like we did example number 4. That is example number 4 and the consequences of example number 4. That is we proved actually a to b x dx is b square over 2 minus a square over 2. So in similar fashion, you can prove these two results. And I'll urge you to do it yourself. That will be interesting. So here is the continuous function defined over the closed interval AB, and we have a partition of the subinterval x0, x1 up till xn, and this is the kth interval ck, the point in the kth interval, and this is the height fck. So this is the point in the curve ck fck. If we have to find the average value of this curve, so how can we find the average value? Because we have divided it into n subintervals. So f of c1 plus f of c2 plus we have n values divided by the number of values. Now, if this is equally spaced, then delta x, the length, this length of the subinterval, kth subinterval, is delta x b minus a over n, as shown. So n here is from this result we can find the value of n. So n here is b minus a over delta x. Okay, so 1 over n is delta x over b minus a. So we can replace now. What is this? fc1 plus fc2. This is actually sum of fck. K varies from 1 to n, and n is replaced by the value delta x over b minus a. And if we take delta x inside, and then we have, this is the area under the curve, okay, above x-axis, and this is the length of the interval AB, b minus a. So we already have defined the area in the previous sections in terms of these Riemann sums. So let's define the area in terms of integrals, definite integrals. So here is the definition of average value of the function in terms of definite integrals. If f is integrable on a closed interval AB, then its average value in AB, and this is also called the mean of the function. It is actually area divided by b minus a. So we just came to know that area is equal to area under the curve. We have so area under the curve above closed interval AB is given by this integral. So that is area over b minus a. Okay. So you just have to remember this definition, that area, average value of a function in the interval closed interval AB, is integral of fx dx in the interval ab from a to b divided by the length of the interval. Okay, and of course this is very important, that if f is integrable. So find the average values. There is an example. Find the average value of fx is equal to square root of 4 minus x square on the interval minus 2 2. So what we need to do, in this case our AB is minus 2 and 2 respectively, and our fx is square root of 4 minus x square. So what we need to do, we have to integrate this function on the interval minus 2 to 2. This will be in fact area, and then we'll divide it by the length of the interval, which is 2 minus negative 2, that is 4. Okay, so this will give us the area, average value of the function. So first of all, find the area under the curve. Okay, uh, so this is in fact when we have y is equal to 4 minus x square, that is fx is equal to 4 minus x square, means the height is equal to 4 minus x square. So this x square square root, so this gives us y square is equal to 4 minus x square, and this gives us x square plus y square is equal to 4. And what is this? This is the equation of circle with center at origin and radius 2. But this square root shows that this is the upper part of the circle which lies in upper half plane, right? So this is the semicircle like this, which lies in the upper half plane. This is this semicircle. So if we had negative sign here, so circle shown, the circle could be shown below x-axis. Okay, so above x-axis shows that height is positive, and since height is positive, so all the values of the function lie above x-axis. Actually, this y is equal to square root of 4 minus x square at the heights of the this semicircle with the radius 2 and center at origin. So we can find the area directly using the formula for area, that is pi r square. Pi r square gives us, since r is 2, so pi r square is 4 pi, and as this is semicircle, so area of this region will be divided by. Okay, so this will be 2 pi. Okay, this is the one way. Other way is that we have to integrate this function from minus 2 to 2. This will also give you the value 2 pi. Okay, so the average value is area divided by the length of the interval. Area is 2 pi, length of the interval is 4, so 2 pi over 4 is equal to pi by 2. So this is the average value of the function, which is pi by 2. And that's all for this section. We'll see you in the next lecture with a new topic, with a new section. Till then, take care. Bye-bye.